Yo guys, have you ever wondered how do they even measure the flow rates coming from pipes in fluids, mainly water and air? And have you ever saw that weird looking shape in an airplane? In this video, we will find out what is a Venturi meter and the Pitot tube, including its history, construction, working principle, and the most important, the application and the formulas behind it. Me and my group mates will discuss it. Enjoy!
The Venturi meter. The Venturi effect was discovered by Italian physicist Giovanni Battista Venturi, who lived in between 1746 and 1822. A Venturi is a system for speeding the flow of the fluid by constricting it in a cone-shaped tube. In the restriction, the fluid increases its velocity, which reduces its pressure and produces a partial vacuum. As the fluid leaves the constriction, its pressure increases back to the ambient or pipe level. Venturi meters are flow measurement instruments which use a converging section of a pipe to give an increase in the flow velocity and a corresponding pressure drop from which the flow rate can be deduced. They have been in common use for many years, especially in the water supply industry. Ito naman yung construction ng Venturi flow meter. Kung makikita natin, syempre merong inlet, may throat, may outlet section, tsaka may pressure taps. Ito naman yung working principle ng Venturi flow meter. May inlet section, which is yung converging cone. Yung shape niya is gradually narrowing. Syempre, yung function niya accelerates the fluid as it enters, causing pressure to drop and velocity to increase. And sa throat naman, yung shape niya is the narrowest part of the tube. Yung function naman niya is the fluid reaches its maximum velocity and minimum pressure. This is the critical zone for measuring pressure differences to determine the flow rate. Sa outlet section naman or diverging cone, ang shape niya is gradually widening. Yung function naman is slows down the fluid, allowing the pressure to recover without causing turbulence. And yung pressure taps naman or ports, yung location niya is one at the inlet and meron din sa throat. Yung function naman nito is used to measure static pressure at different points to calculate the pressure difference. And flow tube and main body naman, ang material nito is usually metal or minsan plastic, depending sa application. Function naman nito is houses the Venturi structure and directs the fluid for the required profile. And add-ons lang, manometer or differential pressure sensor, ang function naman nito is connected to the pressure taps to measure the pressure difference, which is used to calculate the flow rate using Bernoulli's equation.
So why do we use a Venturi meter? We use the Venturi meter mainly because it gives us accurate flow measurements by applying Bernoulli's principle, which relates the drop in pressure to the increase in fluid velocity. It also has low energy loss compared to other flow meters like orifice plates, thanks to its smooth, streamlined design. Another advantage is that it has no moving parts, making it durable, low maintenance, and less likely to break down. Lastly, it's versatile. It can handle clean or dirty fluids, liquids or gases, and even suspensions, which is why it's used in water treatment plants, oil pipelines, and chemical industries.
Ngayon is tatalakayin natin ang iba't ibang application ng Venturi meter sa iba't ibang industry. Ang Venturi meter is isang device na ginagamit para masukat ang flow rate ng fluid sa loob ng pipe. Pwedeng liquid o gas. Napaka-efficient nito at commonly ginagamit dahil sa high accuracy at low energy loss. Narito ang ilan sa mga wide range of applications ng Venturi meter. Number one is industrial process control. Sa mga water distribution ay sa mga factories or manufacturing plants, ginagamit ang Venturi meter para i-monitor at i-control ang fluid flow sa iba't ibang proseso. Halimbawa is sa food processing or oil refineries. Kailangan ng accurate measurement ng liquids para hindi masayang ang raw materials. 2 is water supply systems. Sa mga water distribution network is tulad ng munisipyo or barangay water systems, ginagamit ito para masukat ang flow ng tubig sa mga main pipeline. So, nakakatulong ito para i-maintain ang tamang pressure at maiwasan ang leakage or overflow. Number 3 is chemical plants. So, sa mga chemical industries, kailangan ng precise movement ng fluid, measurement ng fluid para sa mga chemical reactions. So, dito mahalaga ang Venturi meter para masigurado ang safety at efficiency ng operation. 4 is sa irrigation system. So, sa agriculture, ginagamit ang Venturi meter sa mga irrigation systems para mas kontrolado ang pagdaloy ng tubig na pupunta sa mga taniman. So, nakakatulong ito para hindi mas sayang ang tubig at ma-maximize ang ani ng mga magsasaka. And last is aircraft engine testing. So, syempre, pati sa aviation industry, ginagamit ang Venturi meter para sukatin ang airflow sa aircraft engine test. So, mahalaga ito para masigurado ang performance at kaligtasan ng mga makina ng aeroplano. So, makikita natin na ang Venturi meter ay hindi lamang basta measuring device. So, isa itong mahalagang bahagi ng iba't ibang industry. Mula sa mga simpleng irrigation system hanggang sa complex aircraft testing. So, reliable at versatile talaga ang gamit niya.
Now, we discuss the Pitot tube. It is a device used to measure fluid flow velocity. In the history, it was invented by a French engineer, Henri Pitot, in 1732. So, it's not a modern device. He initially used it to measure the velocity of water in rivers and for application in aqueducts. The modern form of the Pitot tube, enhancing its accuracy and applicability, was developed by Henry Darcy in 1858. A Pitot tube is a cylinder with one end open and the other end closed. The fluid streaming through the pipeline enters the Pitot tube and rests there. Another section within the Pitot tube is filled with a fluid with a static pressure. A diaphragm separates both chambers. To further explain the Pitot tube, we have its construction. Here, we can see that it consists of two hollow tubes that measures pressure at various places within the pipe. One tube gauge the impact or stagnation pressure, and the other tube measures only the static pressure, usually at the pipe wall. These hollow tubes can be mounted separately in a pipe or installed together in one casing as a single device. For the working principle, the Pitot meter comprises a tube that is directed towards the flow. The fluid penetrates through the impact hole, and apart from this, there can be two more holes in the Pitot tube that acts as static pressure sources. To further explain the working principle of the Pitot tube, we can simply discuss the parts of it. First is the impact or the stagnation tube. In position, it is faces directly into the fluid flow. The fluid is like that, directly. It measures the total pressure, or in fluid mechanics it is called the stagnation pressure, which includes the both static and dynamic pressure. Now, for the second part, is called the static ports or the side holes or tube, which is positioned located on the side of the tube perpendicular to the flow direction. It functions because it measures the static pressure of the fluid at pressure exerted without the flow movement. And next is the inner and outer tubes or the combination tubes. Some Pitot tubes combine both the impact and the static pressure tubes into a coaxial design. In inner tube, we have the carrier of the stagnation pressure, and in the outer tube, we have the side holes to carry static pressure. And next is the pressure connections, which function that there are the outputs that connect to a differential manometer or pressure transducer to measure the pressure difference. One line is for total pressure and the other is for the static pressure. And to support the Pitot tube, we have the mounting stem or the support rod, which supports and positions the Pitot tube in the flow. Sometimes it allows for movement or alignment adjustment. That is from the construction and the working principle of the Pitot tube.
So why do we use a Venturi meter? We use the Venturi meter mainly because it gives us accurate flow measurements by applying Bernoulli's principle, which relates the drop in pressure to the increase in fluid velocity. It also has low energy loss compared to other flow meters like orifice plates, thanks to its smooth, streamlined design. Another advantage is that it has no moving parts, making it durable, low maintenance, and less likely to break down. Lastly, it's versatile. It can handle clean or dirty fluids, liquids or gases, and even suspensions, which is why it's used in water treatment plants, oil pipelines, and chemical industries.
Ngayon is tatalakayin natin ang isa sa mahalagang device na ginagamit sa fluid flow measurement. So, ang Pitot tube. So, ang Pitot tube ay isang instrument na ginagamit para sukatin ang fluid velocity, usually ng air o tubig. Simple pero very effective ito at widely used sa iba't ibang fields. So, narito ang mga main applications ng Pitot tube. Number one is aviation. So ito sa pinakamahalagang gamit ng Pitot tube. So sa aeroplano, ginagamit ito para sukatin ng airspeed ng aircraft habang lumilipad. So importante ito sa kaligtasan at performance ng aeroplano. Kung faulty ang Pitot tube, maaaring magbigay ito ng maling speed reading. So ito is napakadelikado. Number 2 is wind tunnels. Sa mga wind tunnel experiments, ginagamit ang Pitot tube para sukatin ng bilis ng hangin habang tintest ang mga prototype ng sasakyan, aeroplano at iba pang mga vehicles. Mahalaga ito sa aerodynamic testing. Number 3 is HVAC systems. Sa mga HVAC systems, ginagamit ang Pitot tube para i-measure ang airflow sa ducts. So, nakakatulong ito para ma-optimize ang system at siguraduhin efficient ang air distribution sa buildings. Number 4 is water flow in pipes. So, bukod sa hangin, pwede rin itong gamitin sa pagsusukat ng water flow sa pipelines. So, ginagamit ito sa mga treatment plants at industrial piping systems para i-monitor ang flow rate ng tubig. Number 5 is marine vessels. So, sa mga barko o bangka, ginagamit din ang Pitot tube para sukatin ang speed ng vessel sa tubig. Katulad sa aviation, mahalaga rin ito sa navigation at safety ng mga sasakyang pandagat. 6 is industrial applications. So, ginagamit ang Pitot tube sa iba't ibang industrial setups tulad ng chemical plants or oil refineries at power plants para monitorin ang fluid velocity sa mga critical na proseso. 7 is automotive testing. Sa automotive industry, ginagamit ang Pitot tube para sukatin ang airflow sa intake systems o habang tinigas ang aerodynamics ng sasakyan. Makakatulong ito para i-improve ang fuel efficiency at performance ng mga kotse. So kaya makikita natin na ang Pitot tube ay versatile at essential sa maraming industry. Mula langit hanggang dagat. So mula aircon system hanggang racing car. Simple man ang itsura nito, pero malaki ang contribution nito sa science at engineering.
You memorize or familiarize the general formula we use in the Venturi meter and the Pitot tube. This is in our presentation, and also we can distinguish the parameters involved. The formula velocity of the Pitot tube is derived from the Bernoulli equation itself we use commonly in our room or in our lecture. Also, it is similar to the flow velocity, which is square root of 2 gh, the gravity and the height. And in the Pitot tube, V2 is stagnant, which means that it is equal to 0. That's why there's a 0 there. For the height, there's a 0 too, because in Venturi meter and Pitot tube, it is assumed to be horizontal. So there's not much height on it. So if we develop the general formula or derive 2jc G, difference of the height, and G, C, the gravitational constant and the rho density is equals to V1 squared. We also know that pressure in fluid is equals to rho GH over GC, which help us develop the general formula. Now we cancel AC, rho, and V1 squared. Now what we get is 2GH, difference of the height, and V1 squared. In order for the V1 squared to be cancelled, we add the square root symbol. So here we can now, or V1 I mean, we can now also add the coefficient of the Pitot, just like that, and 2GH. Also, we can now add the manometric fluid density and the flowing fluid density, which is -1. This is the formula velocity for the Pitot tube. For the Venturi meter formula, it is derived from the Bernoulli equation, or the derived formula of the Bernoulli equation we use in the room, with the pressure, the height, and the velocity. At the right side, we can see the continuity equation, cross-sectional area of the first multiplied to the first velocity equals to the second, and below it is the pressure in fluid, which is equal to rho GH over GC, or the rho, which is the density. Now, deriving the formula, we get 2GC PG H2 minus H1 equals to V2 squared minus V1 squared over GC. Now, we will cancel GC, gravitational constant, then what we get is 2g difference of the height equals to a1 v1 equal to square minus v1 square. This one we get from the continuity equation if we manipulate the formula. v2 equals to a1 v1 over a2. Now deriving this further, 2g the difference of the height is equals to v1 square and a1 a2 square minus 1. Now next is, now for the v1 we can now add the coefficient of the Venturi and square root of the 2gh and a1 a2 squared minus 1. So we square root that in order for the v1 squared to be cancelled to only get the first velocity or the v1. Now for the final formula of the Venturi, v1 now is to cv and 2g is the height, a1 a2 squared minus 1. And now we can now add the manometric density and the flowing density, or the flowing fluid density, which is rho m over, or the density of the fluid minus 1, or the flowing fluid. This is the formula for the Venturi.
Hello everyone, and we have some sample problems to solve a Venturi or a Pitot tube problem, but we're starting at the Venturi meter first. So let's start with the problem number 1. A Venturi meter is installed in a horizontal water pipe to measure the flow rate. The pipe has a diameter of 10 cm at the inlet and 5 cm at the throat. The manometer connected between the inlet and the throat shows a difference in pressure equivalent to 0.8 meters of water column. When we draw this, when we draw a Venturi meter like this, this is the inlet, this is the converging zone, this is the diverging zone, and this is the throat. And we have a diameter 1 here given is, and diameter 2 here. And also sinabi rin na the manometer connected between the inlet and the throat. So we draw this like this, and shows a difference in pressure equivalent to 0.8 meters. So let's assume this is certain fluid. The pressure head difference here is equal to 0.8 meters. So let's start at the A, velocity at inbound, but first we have to enumerate muna yung given. The diameter 1 at the inlet is 10 cm, also equal to 0.1 meters. The diameter of the throat is 5 cm, also equal to 0.05 meters. The pressure head difference is 0.8 meters. So let's find the velocity at inlet V1. We can use the equation V1 is equal to the square root of 2GH over area 1 over area 2 squared minus 1. We simply plug in the given 2 times the acceleration due to gravity, 9.81 meters per second squared, times the pressure head difference of 0.8 meters, divided by the area of a cylinder, which is pi over 4, diameter 1, which is 0.1 meters squared, divided by pi over 4 multiplied by 0.05 meters squared minus 1. So the computed value of velocity at inlet V1 is 1.023 meters per second. Let me write this. And also we can erase now this solution in A. Let's go at letter B. Velocity at the throat, V2. Ang hinanap dito yung velocity at the throat, which is at maximum. So we can use continue with the equation, which is A1 times V1 times A1 is equal to P2 times V2 times area 2. Since P1 and P2 are not given, so we can cancel this two. And may iwan na lang is V1 A1 is equal to V2 A2. When manipulating this equation, we have V2 is equal to V1 times A1 over A2. So the value of V1 here is 1.023 meter per second times the area of the inlet, which is pi over 4, 0.1 meters squared, divided by the area at the throat, which is pi over 4 times 0.05 meters squared. So the computed value of the velocity at the throat is 4.092 meters per second. And we can erase this one. So when computing the value of flow rate, we can use the formula for finding the flow rate, Q is equal to V velocity times the area. So substituting this, we have 1.023 meters per second multiplied by the area 1, which is pi over 4, 0.1 meters squared. So we have a computed value of the flow rate is 0.0080346 cubic meter per second, but ang hinahanap is in liters per second, so we can simply multiply this by 1000 liters in 1 cubic meter. We can cancel this. So ang makukuha natin sagot sa flow rate is 8.035 liters per second. So that's how we solve such a problem regarding Venturi meter.
sample problem. So, practice problem is, water flows through a horizontal Venturi meter. The diameter at the inlet is 10 centimeters, and the diameter at the throat is 5 centimeters. The difference between the inlet and the throat, measured by a manometer, is 20 centimeters of water. So, i-assume natin na yung water, syempre, ang density niya is 1,000 kilograms per cubic meter. Syempre, yung gravity naman is 9.81 meters per second squared. Tapos yung CV naman, which is yung coefficient of Venturi, is 0.98. And syempre, yung manometric fluid, kasi water siya, is equals to 1. So, ang hinahanap is, find the velocity of the water at the throat, which is yung V2. So, syempre, bago mag-start ng solving, need muna natin isulat yung formula, which is V2 is equals to CV times square root of 2G times height difference times A1 over A2 squared minus 1. So, para masimulan na yung pag-solve, syempre, need natin i-convert yung diameter sa area. So, 10 centimeters is equals to 0.10 meters. And yung formula naman area is pi d squared over 4. So, pi times 0.10 squared over 4 is 7.854 times 10 raised to negative 3 square meters. And syempre, sa dito naman, parang yung sa una lang, 5 centimeters is equals to 0.05 meters. And same method lang, pi times 0.05 squared over 4 is equals to 1.963 times 10 raised to negative 3 square meters. So, nakuha na natin yung D1 and yung D2. And next naman is, ipa-plug na natin yung values sa formula. So, V2 is equals to 0.98 square root of 2 times 9.8 times 0.20. So, ito yung 20 centimeters kanina sa height. Na-convert na natin sa meters. So, continuing, times 7.854 times 10 raised to negative 3 over 1.963 times 10 raised to negative 3 squared minus 1. So, pag na-simplify na yung loob, ang kalalabasan niya is 58.86, which is yung final answer is 7.52 meters per second.
Oh, hi guys. Ngayon, mag-solve naman tayo ng simple Pitot tube problem. A Pitot tube measures air velocity through a duct. So, alam na natin na yung air is the flowing fluid. The height difference of the head is 20 cm in H2O. Now, we all know that H2O is basically water. The coefficient of the Pitot tube is 0.95. So, lagay natin 0.95. Now, if the density of air in the water is 1.69 kg per cubic meter and 1,000 respectively, find the velocity of air. Sa Pitot tube, alam na natin na yung general formula is pagkuha ng velocity is ganito. 2h and manometric density over yung flowing fluid density minus 1. Ayan. Normally, mas mataas talaga yung manometric fluid density kaysa sa flowing fluid density. So, ito is yung mas mataas na density, which is the water. And ito naman yung air. Ayan. So, substitute lang natin 0.95, yung coefficient 2, and gravity nasa SI tayo, so 9.81 meter per second square. So 9.81 second square. And yung difference sa height, which is 20 centimeter, ko-convert natin yan sa meter. So 100 centimeter. And now, yung density na dalawa, 1,000 kilogram per cubic meter to. And 1.69 minus 1. So, parang di nakakasya, pero okay lang. Kapag kukumpitin natin yan using our calculator, which is in-input ko na, direct substitution lang yan. Except kapag may mga conversion. So, ayan. Equals natin. So, ang nakuha nating velocity ng air is velocity of air is equals to 45.738 meters per second kasi we are dealing with velocity.
So, from the figure shown, determine the velocity of the stream of water. So, as you can see, yung fluid na of a flow dito sa stream is water. So, since ito ay stream, exposed ito, yung upper part na dito is exposed sa atmosphere. Yes, then this is open sa atmosphere. So, since the water is flowing, my velocity is stream. And yun yung kailangan natin i-determine. So, pag i-determine natin is we will use the Pitot tube, which is this bent tube. So, from our derivation, so this is the equation of the Pitot tube. So, Vt is equals to square root of 2gh. So the given is this 80, the height is 80 centimeter. I-convert natin into meters times, so 1 meter is equals to 100 centimeter. So 0.8 meter siya. So since walang coefficient of velocity, walang given na coefficient of velocity, ang mahanap lang natin is the theoretical velocity, which is this. So kukumpit na natin. So Vt is equals to square root of 2 times the gravity, which is 9.81 meters per second squared, times the height, which is the na kinumpit natin kanina, which is 0.8 meters. So lagyan natin sa calcu. So 2 So the velocity of this stream of water is 3.96 meters per second.
That's it for our video for Venturi meter and Pitot tube. I hope you enjoy it and like it. Please subscribe and like, share with your friends or classmates. Thank you. See you next time. Woo!